The Army, the Air Force, the Department of Defense agencies, they can use it for, creating realistic scenes of for simulations. They use it for scanning heads to create custom helmets. They use it for custom body protective armor, especially women. That was a big problem in the past, where not one size fits all for women in terms of protective gear. And 3D scanning can go a long way there. Imagine walking into a mall, stepping into a booth and getting your body scanned, and all of a sudden your measurements are sent to all the stores that you want to, and they have your measurement, and now you can get form-fitting clothes. I mean, it goes a long way. It goes a long way in terms of the possibilities of the system. It opens doors to do things more easily.
How's it going, everybody? I want to welcome you to another episode of Trade Secrets by Tripletote. Today, I have a guest who's done some astonishing things. He's a real good friend of mine. His name is Nasir, and I want to get you guys a chance to check out his journey. And his personal background is very interesting, and he has been able to really do a lot of things on his own, self-taught. And that was the biggest contribution I felt he could add to the podcast, because he's really accomplished a lot. And again, he was all self-taught. How's it going, Nasir?
Good. How are you? Thanks for having me on, Antwaine.
Appreciate you coming on. Now, just to take it back to the beginning, I guess you're not originally from the U.S. You're from London, right?
Yeah, I was born in London, in the UK, and then the family moved here to the U.S. When I was pretty young. So I did most of my young growing up here in U.S. and then for high school, I basically moved back to UK. So I studied, did over there. They have a system called GCSEs, which is the year's equivalent of high school that you go through here. And then when I came back to the US, I went right into University of Connecticut, and I did my undergrad mechanical engineering, and then I went to Rensselaer here in Hartford, and I did my graduate master's degree in mechanical and software engineering.
Now, when students take up that major of mechanical engineering, there are certain fields that they normally go into. Did you envision yourself doing a traditional route of when it came to a career, or did you just want the abilities and tool set that came with becoming a mechanical engineer?
Well, originally I was really interested in math in school. It was one of my favorite subjects, math and physics. I actually had a really good physics teacher in when I was studying GCSEs in UK. He had a way of teaching which was it just clicked with me. We do things where even as simple as putting a car on a ramp, a little toy car, and letting it go, and seeing how far it goes, and it matched very closely with the calculation that we had done on the board. And I thought it was pretty amazing that you can, being able to predict things so accurately before they happen based on the laws of physics was very intriguing. And I got into engineering because in my studies, that kind of was the engineering to me is solving a problem. It's you're solving a problem to make human life easier. In the essence of engineering, and what I like to do is to make human life easier. And engineering is a way that you use physics, you use math to come up with a solution to a problem. For example, if you want to get from point A to point B, you can take several different technologies to get there. You can go in a car, you can go in a train, you can go in an airplane. They all have different modes of transportation, but they're all originally designed to get you from point A to point B. The way in which they do it and the technology around how that is accomplished is something that's it's something that intrigues me. It's something that I want to be in, and it it's kind of how I think. I like to get into how things work. Why does that particular thing, even in nature, why does that particular process happen? I just kind of my mind is very inquisitive, and engineering is a way to kind of follow the natural order of things, the natural laws that are there in nature, and you're kind of using that to create things.
Now, so after after being in class with this physics teacher who kind of introduced you to these concepts,
Yeah.
from there, just knowing you, I know you became just a diehard person when it came to trying out your own experiments, like, or doing programming or doing code or trying to make scanning or algorithms work. You will put in a lot of hours doing that, even outside of what you were required to do.
Right.
How did you connect your drive to the physics or to learning and math? Did you always have the drive, or did the physics bring it out of you?
I mean, the physics brings it out. I grew up with 4 younger brothers. My father himself was an engineer, and the way that we would, our activities as young children, we would put we'd put a propeller on like a toy car, and put a battery in it, and put it down on the floor and let it go. And there was, we also we had a lot of art activities with my father as well. I remember we used to sit down and draw and paint, and it seems to be just a family inheritance that I have from the artistic side. This underlying need to create, I think, is what drives me the most. I like to create things, and whether you think of that from the artistic side, you have a blank sheet of paper, and by the time you're done, either drawing or painting, you've got something that you created on that sheet, right? And if you're creating a technology, you're starting off with sometimes nothing. Sometimes you're starting off at at some base level technology, and then you create something out of it. And I think it's, if I really get the words right, I think it's the need to create that I really enjoy. I like to make something. I like to see it work, but I also like to learn from its failures and then make it better. And what that does to me is, when something fails, for me, it's kind of an opportunity to learn, okay, what went wrong? You look into it deeper, you learn from the mistakes, or you learn how to make something better, and you do it, and then you watch it work again, and then you continuously learn from that process. Whatever you create, you're basically looking back at it like, how can I improve it? How can I make it better? And it's that drive. It's that, wanting to make something perfect, let's say, is something that keeps me going.
Now, a while ago, you able to really format everything you were working on into jumping in front of the cutting edge on different technologies, like specifically the white light scanning. You were able to figure out that this was emerging. And I think what I picked up from that is, just knowing you, is that you jumped in head first. You were able to get the resources to experiment with the the process of doing the white light scanning, the no contact scanning, and you were able to bring something about literally through trial and error. Like, your version 1 came, then your version 2, how did you feel up against the clock of technology when you were developing that thing, trying to beat it to the market by developing it yourself?
Well, at the beginning, I saw a need, and I have my, the personal interest in, creating different technologies. The need that was out there was to improve, measurements. The time it takes to take measurements specifically, not to improve measurements themselves, but to decrease the time it takes to measure something, and being able to kind of capture physical objects and digitize them kind of quickly. I mean, we can take pictures of things, and that's a couple of milliseconds, and you get a 2D snapshot of a part, or of an object, or whatever you're taking a picture of. So why not? How come we can't? Is that workflow possible with capturing 3D geometry, with the actual 3D? So at that time, there were 3D scanners out in the market. There's the laser scanners, and there was a few structured light scanners, and but the traditional technology was it's called photogrammetry. You just had two cameras, and just the way the human perception is. You have two eyes, and you have that depth via the your two eyes focusing on one specific, the same particular object. And it's that process of fixating on one object. It's triangulation. I mean, you've got the distance between your eyes, and then you have the distance of the object between from each eye. And all these technologies are based on that. But what I found was that the technology was cost prohibitive for the kinds of people that I was in contact with. A lot of these folks were kind of starting their companies. They were or running companies, small, medium-sized businesses, and the technology was $50,000 to $100,000. And in fact, if you went with the high-end systems, they were up to $200,000. And although the technology price is justified, especially when you get it into the capabilities of some of these high-end systems, for companies that want to, that wanted to move past their old way of doing things, hand measurement with height gauges or calipers or what have you, they didn't have any choice but to cough up the funding to purchase these things. And for me, I'm looking at this problem like, okay, well, I can get a laser line generator for $30, and I can use a webcam for less than $100. And can we come up with a solution to capture objects in 3D? So the first system that I made was a laser-based scanning system, and a laser line would sweep across the scene, and the camera would capture the laser line as it was deformed when that laser line hit the object surface. And from that deformation, you can calculate the 3D surface if you know the distance between the camera and the laser. So even it was pretty basic when you think about it, and I put together a software, and I was capturing objects. So there was improvement needed, obviously. I learned that the thickness of the laser line, affected the resolution and, the accuracy of the scan. And so eventually the laser line generator, changed, and the webcam changed to a machine vision camera. And suddenly we were, capturing very accurate, high resolution scans.
So let me ask this.
Yeah.
Sorry, let me ask this. So, two questions, kind of back to back. So what did you bring the price down to? Like your machine, if you compare it apples to apples, I know there are probably some high-end machines that had some capabilities that yours may have not had, but if you just compared apples to apples, what did you bring the price down from? Like, what would a person pay from an established company, and what were you selling the product for? How were you giving them a discount?
Basically, our systems were 10% the cost of a comparable commercial system. So if a system costed $100,000, ours costed $10,000.
Wow.
If a system costed $200,000, ours costed 20. If it costed 50, ours costed 5,000. The reason we did that was because we essentially took the problem off of the hardware. With 3D scanning, you often have, and in most situations, I mean, the hardware kind of dictates, you know, a lot, if not all, of, you know, how that a 3D scanner functions, how accurately it can capture scans, the resolution that it's going to capture at. And we tried to, you know, I wrote algorithms that that allowed, you know, a scanning system to be built with lower priced, lower quality hardware, but still capture, you know, high resolution and high accuracy scans. So we came up with calibration algorithms. We came up with, you know, super resolution algorithms. We came up with, you know, filtering, all these different steps that once you capture the data, it goes through all these processes and it outputs the best quality data that it can. You know, in one instance, a particular system was capturing several images. Instead of just capturing one and calculating off of that, we were capturing several and then averaging and then doing some, you know, noise filtering and things like that on those sets of images to create the single scan. So coming up with solutions where, you know, if you do it in software, you release the requirement for the hardware to be expensive. And so now we can use commercial off-the-shelf, readily available hardware and just connect it with the computer, and our software would control it. And you know, the software had the ability to calibrate, you know, like a camera system, a projector, to be used as a structure light scanner. And
now let me ask one very important question with all the information you've given us is, can you tell us just what are the practical applications? Like, what is the average private company or the military actually using your equipment for, or using white light scanning and measurement for? What from a human, you know, from just a regular layman point of view,
yeah,
what don't they see that you have affected or that your industry affects when it comes to what you guys do?
Sure. I mean, structure light scanners, you can think of them, I mean, they are 3D cameras. You capture an object, you get the 3D definition of that object. So just imagine what you can use cameras for and extract that to 3D. So the most used, the problem that I tackled was quality inspection, being able to digitize physical parts to compare them against their original CAD design and see if they're made correctly. So, you know, manufacturing companies could very quickly image a part and know, you know, if it meets spec, and if it doesn't, where does it not meet spec? You know, what needs to change? You can use it in healthcare for prosthetics. You can use it for dental industry. You know, you can use it for architecture, artists, you know, designers, for example. You know, a lot of car manufacturers, they even some of them still use the clay models for prototyping, and you digitize that, and then you can build a model from that digital, you know, that scan data very quickly. You know, nowadays you have very high, you know, very you know, accurate, high resolution computer graphics in the entertainment industry. You see it in movies all the time now. CGI, you can capture physical objects and much more quickly than you can model them. You know, it goes a long way. The technology it can be used to help in every single industry. You know, the medical industry is very interesting because medical industry has been using 3D scanners for a long time. I mean, they have the CT scanners, they have the MRI imagers, they have, you know, different technologies that some just do 2D imaging, but when you start to get into 3D, you start to help solve a lot of problems. Imagine if somebody needs a brace on their arm, or somebody needs a prosthetic. You can very quickly scan, patients and create form-fitting, braces or form-fitting prosthetic pieces, and that's very important because it kind of gets into the comfort for the patient. If the more comfortable you are, the more natural it is, the quicker you recover, and it's to do with your mindset as well. It's to do with your mental recovery on some things as well. I mean, if you're uncomfortable, that affects you. The Army, the Air Force, the Department of Defense agencies, they can use it for creating realistic scenes of for simulations. They use it for scanning heads to create custom helmets. They use it for custom body protective armor, especially women. That was a big problem in the past, where not one size fits all for women in terms of protective gear, and 3D scanning can go a long way there. Imagine walking into a mall, stepping into a booth and getting your body scanned, and all of a sudden your measurements are sent to all the stores that you want to, and they have your measurement, and now you can get form-fitting clothes. I mean, it goes a long way. It goes a long way in terms of the possibilities of the system. It opens doors to do things more easily, and so you can get to the level of customization and the one-offs now, instead of doing things in batch mode, especially now with the with the 3D printing technology. That's how these two go hand in hand, and the possibilities are really endless if you really think about it.
Wow. Now let me ask, what's on the horizon for you? Like, what things are you looking forward to in the next 24 to 36 months? Like, what projects or products are you looking forward to working on or bringing forward?
Right now, traditionally, our scanners have been a standalone system where, they've you put either on a tripod or a mono stand, and you aim it at a certain area, and you can have a rotary system or some kind of a positioning device. So you put the object on the positioning device, and you just take scans. So if there's some process that's happening, you'll take the part off that process, bring it to the scanner, excuse me, scan it, and then do something with it. Now we're getting into this. We've done a lot of integration with machines. Now we're trying. The thing that I want to do with the way technology is headed, everything is being connected together through the internet. So this is the Internet of Things. And we want our device to be seen as, our scanners to be seen as a 3D sensor, a smart sensor that you can connect with any device. And that sensor will give you the needed 3D and color feedback that would be needed for further processing of whatever you need. For example, if you want to scan, instead of doing facial recognition on images, you can do facial recognition on 3D images. If you wanted to do if you wanted to do inspection on the machine, you can put the sensor on the machine, and the machine can actually control that sensor as a 3D camera and actually take pictures of the object and tell you right away whether or not that object is good or bad. Without, now we're going from taking this part to the scanner to bringing the scanner to the part.
Gotcha.
Yeah, and that's very exciting, because now, it with that, we're communicating with all the other devices that are open for communication, and there's this nice data stream going into a central processing unit, or as now more and more companies are getting into this, the AI or machine learning. We can help provide the 3D information, high resolution, high accuracy 3D information that's needed in so many applications.
Now, your company is called M3DI. Where can people find out more information about you, your company, and what you guys are doing?
You can go to our website, m3di.co. We have information listed on there about our services and the scanners as well. You can also go to simquest.com. Simquest-inc.com. So that's CIMQUEST-INC.com. They're a distributor of ours. You can go on their website and look up the Varascans, VARSCAN. And you'll see the different models there. But you know, we're really available pretty much on if you know, we've got YouTube videos up, so if you want to look up M3DI on YouTube, you can find some videos there. But yeah, the website would be the best place to reach us.
Awesome. Hey, I want to thank you again for coming on the show, especially at such short notice. I see we're working out of your car. That's how flexible you are, helping us out, putting this show together. So thanks a lot for stepping in last minute. Not a problem. I appreciate you having me on. Hey, and thanks to all the viewers, listeners, and readers of the podcast. I thank you guys for your support. And as again, I'll put the links to Nasir's website and some of the videos that he has inside this posting, so you can easily click to get there. And we'll see you guys soon on the next episode of Trade Secrets. Have a good day.